Hello, I'm Mike Rutland. I do lots of low-level Arm64 bits, and I've somehow got involved in live patching. Right, so a lot of people are asking about live patching, and it's been around for a while. People have been asking about it for a while, so where is it? Well, the fundamental thing everyone's realized is we need reliable stack trace. So of course, that's what everyone's trying to work on. Unfortunately, that's actually the last thing that we need to enable because it depends on a huge number of other things aligning such that we can actually implement reliable stack trace. So for the last few years, we've actually done a lot of preparatory work that might not immediately seem related to live patching, but it's preparatory work. So all the work that's happened with ftrace, so stuff that Torsten from SUSE did with -f patchable function entry, so stuff that we did since then with ftrace with regs, with ours, with call ops, so we can do the actual patching reliably, and so we can actually do the actual patching quickly. And that latter part does actually matter a lot. We've done a bunch of things like we figured out the way that exception table fix-ups across the kernel worked was completely unsafe for reliable stack trace on pretty much all architectures. So we had to come up with a new mechanism for doing X-table fix-ups out of line. So we implemented that on Arm64. X86 followed suit. A bunch of other architectures are using that now. That's things. And a bunch of various things like templated unified entry assembly, narrowing down the problem for the bits that we know we're going to have trouble dealing with, like annotations in assembly for how to unwind those. So there's a lot of stuff that we've actually done, even though we haven't enabled reliable stack trace yet. And there are still a few things that we need to do. The big one that everyone is aware of is we need to figure out how to unwind across exception boundaries. This is why people keep on trying to attack with optool and all that sort of thing to give us that information. There are some gaps in ftrace and krepro trampolines where we know that there is a small window where we can't actually recover the return address. That's possible to fix. No one's done that yet. I have a plan. Hopefully we can get that done soon. False positives and no return functions is an open thing. So big problem is when the unwinder is unwinding, if it gets to a no return function, that no return function has a return address because of the way the architecture works. It's just there is something there. We're never actually going to return to that, but the unwinder thinks we will. And without metadata to distinguish that, the unwinder thinks we're going to return to something. Because of the way compilers generate no return functions, typically they will generate a regular call, which will be a branch and link on Arm64, into the no return function. No return function just like trails off the end. Sorry, and the caller just trails off the end because it knows it's never going to be returned to, so who cares what's next? And there'll be another function next. And so the unwinder believes that we're about to return into the next function, no matter what that happens to be. And that is a problem for live patching because for the consistency model, when we go and check which functions are still active, we'll assume that next function is active when it's not. Josh.
Yes, so one way to deal with that is if you know it's a call frame as opposed to an exception frame, the unwinder can subtract 1 from the instruction pointer always.
Yeah.
So it's looking at the instruction, the call instruction.
Yeah, so that is one thing that has been proposed on Arm64, but we don't always know that without metadata. So I'm just saying it's an open problem that we need to come up with a solution for. And obviously we've got assembly functions and trampolines that are not regular calling convention compliant. And we need some way of dealing with those, whether that's metadata or somehow rewriting them to be compliant. We can't do that in all cases because exception entry, early head.s type thing just simply cannot do that. So we need to come up with some solution for that. For those of you not familiar with Arm64, I just want to explain why unwinding across exception boundaries is painful. Because people think this is a lot easier than it is, and even if we have metadata, it's still painful. So on x86, the return address gets popped onto the stack by a call instruction. You do your thing, and eventually ret pulls it off the stack. On Arm64 and other architectures that have a link register, our call instruction is actually a branch and link. It moves the next instruction pointer into the link register and then branches to your function, and your return actually consumes the link register and goes back. Obviously that doesn't nest, so the function that you've called has to go and save that link register onto the stack somewhere. Our calling convention puts it into a thing called a frame record, which is pointed to by the frame pointer. That's at an arbitrary location within your actual stack frame. but there's a linked list and we can go and consume that. At function call boundaries, it's well defined. Your link register is your return address. The frame pointer points to your parent's frame record. That contains its return address and a pointer to the next one, the next one, the next one. So unwinding at function call boundaries is actually really simple. At exception boundaries, we don't know which of the two to look at. If we look at the link register and we assume that's if we look at the frame pointer and we assume that's the first thing we should wind from, if the interrupted function hasn't saved its return address yet, we've just lost a return address. We might go and patch something that isn't safe to patch yet for the consistency model. If we start from the link register is permitted to contain garbage between saving and restoring it. And so we might get a false positive and assume that something's there that we're about to return to when we're not going to return to it. That is bad for the consistency model because we can just get stuck indefinitely, assuming that we're about to return to something that we're trying to patch, even though we're not, because we could be in a tight loop. One of the proposals for Arm64 was just don't unwind reliably across exception boundaries. But I think practically speaking, that is not workable. Everyone has looked at the proposed preemption changes recently, getting rid of voluntary preemption or making that happen lazily. We'll know that that's going to mean that most preemption is going to happen across an exception boundary. And if and when that happens, even if we sprinkle conned reshared calls everywhere just for live patching, it's going to be painful to maintain. It's just not going to be practical. We also need to unwind across exception boundaries because it makes it much faster. We don't have to go and wait for a task to make some progress, return from an exception in order to discover that it wasn't in the function we cared about. So it makes it much simpler and much faster to iterate over all processes. And also we want to unwind across exception boundaries because real humans need that information anyway. Currently when we panic or dump backtrace, whatever, we are missing information and it's confusing people. People want that. People want it for perf unwinds and things like profile guarded optimization type thing. Yep. Got my print here.
So Mataban from our team posted some patches.
Yep.
Previously, like some months ago, that he's not able to attend today, but he's on the.
Yeah, I was going to talk about.
Yeah, so he says that I asked him. He said his patches do this correctly.
I will get to that.
Okay.
So that's why we need to. That's why we need to unwind across exception boundaries. So I just wanted to get that across. The next thing is how we actually do that. There are two ways in which we can do that. One is to have some metadata to tell us when you go and look at the program counter, where is the actual return address. The other is to force the compiler into generating code in a particular way such that we can look at the PC and just know where the return address will be. Practically speaking, we need metadata. On x86, this is done with objtool. But using objtool, which was the approach that Madhavan Venkataraman proposed, is something we'd already knacked years ago. The reason for that is it relies on reverse engineering the control flow from the binary. This is not maintainable going forwards because we know that the compiler code generation is changing. It changes all the time. New instructions get added, new control flow sequences get added, new things change kernel side. And on the Arm64 side, our code generation has been changing more over the last few years than on the x86 side because we're a relatively newer architecture. And so we just don't want to get into that at all. So back in 2021 at this objtool Arm64 talk, we'd asked for what can we get from the compiler side. Unfortunately, at the time, we didn't really get much feedback from compiler, so we didn't really get that involved in talking, but Ingeberg's S-frame stuff actually looks like that might provide exactly what we need to do this. So that's, I think, what we're going to be looking at for Arm64 going forward, because that comes from the compiler, assuming the compiler doesn't have a compiler bug. Yep.
Yeah, this is perfect for C code. Well, how do you deal with manual written assembly?
We are perfectly happy to write the annotations for manually written assembly ourselves.
Oh.
Sorry, there's two things for that. There's two things. One is that we're trying to get rid of as much assembly as possible on Arm64. And two is that when I say we are perfectly happy to write that ourselves, if we have to write tooling to consume our own handwritten assembly, and we're in charge of that tooling, it's much easier to keep that in sync than it is to keep that tooling for consuming something that someone else has written, right? The key property that we want is that whoever writes the generates the instructions, generates the unwind information associated with that. So if the compiler is generating the instructions, we want the compiler to generate it. If we're generating those instructions, we want ourselves to be in charge of generating that. And if we're delegating that to a tool that we've written, that's also fine, right? But we're keeping those concerns in the same place, and that's the critical property that we want. But good question, I appreciate.
Doesn't user space have the same problem unwinding through signals? Sorry. Doesn't user space have the same problem unwinding through signals?
Yes, user space does have the same problem unwinding through signals, and there is existing ways of handling that with Dwarf. I believe there'll be existing, and I believe S-frame for user space will be able to solve the same. Right?
So what we have. Indy, you ready?
Yes, for S-frame, I've been thinking about it. I think we do need the annotation that these specific frames are signal frames. We don't have this in V2, but it looks like we do need it. So next version.
Okay.
Yeah.
Sorry, and I have some things to ask for S-frame later. Okay, so that's why we do need to unwind across exception boundaries, and why we're not going to reverse engineer the control flow, why we need something from the compiler.
Mark, is S-frame not just a simplified version of Dwarf? I mean, just for the unwinding part. Is it not derived from Dwarf?
It is generated using the CFI sections, and to the question that is it a simplified version of Dwarf? Yes, it's very similar looking to ORC. Does that answer?
Yeah, one of the concerns from one of the reviewers was that Dwarf is unreliable, so that makes S-frame also unreliable. So is there a proposal to make that reliable?
So just to counter that, I think one of the complaints from the Arm64 side is that ORC is unreliable. So I think no matter who's generating this, we need to fix the bugs in generating that.
Yes. Yeah, I think it just boils down to that. It is as unreliable as any other format generated by any other tooling. So
Linux is unreliable.
No, sorry, but this is actually a key thing. I think one of the things we do need to do better between kernel community and compiler communities is actually getting this cross-pollination of, we've discovered this bug, let's go get it fixed.
Yes.
Rather than working around it and forever.
Okay, so with my Microsoft hat on, this is something we're really interested in. Why Madhavan has been working on this. We also know that those patches, there are other companies actually shipping that in production because they need it, kind of large companies. So we would like to know if you can identify anything that we could possibly help with in this. We would definitely look into what we can do to help, and hopefully that's something we can talk about.
Sorry, absolutely. I think one of the key things is, so I know that when Madhavan posted his patches, he said that he had identified a bunch of potential code generation issues or dwarf generation issues, I can't recall which of those. Reporting those bugs to the compiler side would absolutely be a benefit. Testing patches would absolutely benefit. Saying on the list, we want this for this reason, actually reviewing and testing patches would be one of the big things. You can ask a question? Oh, sorry.
Sorry.
And last question, can the Rust compiler generate S-frames?
Can we generate?
What is it doing currently? What do they do currently? Do they generate CFI annotations? Does the compiler do that? So the thing here is, if there are CFI annotations, I think, S-frame generation is at the moment in the assembler, and the interface to the rest of the tooling is CFI annotations. So if the compiler is able to generate CFI annotations for whatever, yeah, so that's it. That's all I wanted to say. If that interface exists and S-frame may be supported. It does, however, also depend on what are those stack frame layouts for those languages. So we need to be also cognizant of that. Yeah, that's all.
So I guess the question, the proxy question could be, does LLVM support S-frame generation, the LLVM assembler? So the Rust compiler will essentially use the LLVM backend to generate code. So once we have S-frame support for the LLVM assembler, we'll have S-frame support for Rust.
Yeah, I think, yeah, sorry. So, like, I think the thing that's important to focus on first of like who supports S-frame is this point about might be sufficient, right? To be crystal clear, to support unwinding out of exceptions, V2 S-frame is not sufficient. Come to the table with V3 and show us that this is the solution, then we will consider if we need to implement this. And the people who care about live patching can help fund the team to do that.
Sorry, just to be clear, the reason I put might be sufficient rather than is sufficient or is not is that I have only just started prototyping the last couple of days, that I know of a few edge cases where I think we can do the right thing. It's just a little bit more painful than we would have liked. I don't know of a specific issue that means it's broken or insufficient. Cool. Final slide. Right. So I mentioned before we did all that other rework as prerequisites, and one of the big things of all of that is that every prerequisite we've done so far is immediately useful. Right. So making it possible to unwind X tables correctly is immediately useful to humans. Making ftrace work better and more reliably, that's immediately useful to humans. Every single thing we've done so far has justified itself on its own merit and been a step towards this. So there's a few things that we want to do quickly in the near term. So passing additional information to the Arch stack walk callbacks, restructuring that so we can pass more information down. We need that for implementing the reliable stack tracer so we can just get at more information rather than we having to implement an entirely parallel Arch stack walk reliable that duplicates all the infrastructure. That's immediately useful for BPF and dump backtrace. So I'm going to try and get that out this merge window. Explicit identification of exception boundaries. That's some changes to the exception entry code so we can reliably say, this is an exception boundary. We know that the next thing is going to be PT regs, whatever. That's relatively simple to do. We want that for dump backtrace and so on. This will not allow us to distinguish whether the LR or the FP contains the actual return address, but it will at least allow us to print them both out and say, this may be the return address. So that we need to go and fix those gaps that I mentioned in the ftrace and krepro trampolines. That is relatively simple, but we need to make some changes to the core code. So it's just so that there's not a window where the return address has been taken off of the shadow stack and hasn't yet been placed into the real return address location. So we just need a callback for doing that in the right place. That's relatively easy to implement. And then the big next thing is prototype the S-frame kernel unwinder. I think on Arm64, the expectation is we're going to do this as a hybrid with our existing frame pointer unwinder, because our frame pointer unwinder works perfectly for synchronous unwinds, but when we get to exception boundaries, we need to go and figure out that difference. We could also use S-frame to validate the synchronous unwind, but there are a couple of edge cases with that just.
So for like dwarf, we typically strip the dwarf data out of the compressed kernel image that winds up on the target. So I guess this would, like the config would say like, if you need to support live patching, like you must ship the S-frame metadata in the
yes.
compressed.
So if you enabled config reliable stack trace, whatever it's called, you get that. My experiment from building that this morning was that for a def config kernel image, this is also about 3.5 megabytes of S-frame information. I don't know how that compares to other things like walk, but
like relative to dwarf, it's probably like 100th the size or something,
yeah.
right? Dwarf's huge.
Yeah, as part of that, we're going to have to identify any gaps we see. So the thing I mentioned earlier about distinguishing no return in cases, I'm not sure. I think S-frame might happen to give us enough information to distinguish that, but I haven't figured out if that is sufficient or not. There are other things that I believe you may know about, but.
For maybe a comment about no return, if you want to discuss that quickly. Yep. So typically the compiler will insert an implicit built-in unreachable after a call.
Yep. I would love for that to be generate a trap instruction.
Yeah, so there's, at least I know Clang has a flag to turn those into traps.
Yep.
And we discussed turning that on just as like a safety thing of like,
so,
what happened if a no return function actually did return?
No, so
something screwy is going on, you probably should just trap.
Yeah, so I would absolutely love that as a safety feature. My understanding, which could be mistaken, was that it was somewhat pessimistic and for functions where you Sorry, my understanding is that it pessimized control flow in other ways, but I'm not immediately certain what I was thinking that was. So,
I mean, I think because you could have other unreachables,
Yeah.
right? Like the programmer could explicitly use built-in unreachable. And so like you don't have fine-grained control in the compiler today to say only turn the no return calls
Yeah.
into traps. It's going to turn all built-in unreachables into traps.
Yeah.
And so like I don't remember the code size difference off the top of my head, but it's like within 1% or something that I think is tolerable. And I think for security, like just turn it on. Something that
I'd be happy to go and just
Yeah.
try that if that's sufficient, and then come back with actual data.
Yeah.
And finally, like as was mentioned earlier, we do need a plan for handwritten assembly. There are going to be sequences which we cannot describe in SFrame because like we have the return address in a different register, and the way the SFrame works today is it's either location on the stack or unknown. So we know that we won't be able to describe that. There are cases we have where that's going to be like in the exception link register, which is a register that only makes sense in privileged code. So this isn't really a generic problem for a tool chain to solve. I think that's something where we're going to have to create our own annotations and our own like kernel specific things for those. But the big thing is we're trying to minimize the amount of cases that we have in the kernel for that. So I think that is going to be manageable. And that's it from me.
Okay, thank you, Mark. We still have time for questions and comments. Are there any?
So would you be using any unwind hints?
So I think we will be using, So yes, I think we'll be creating some hints. I'm not sure that those will be the same as the existing unwind hints that, in my opinion, are largely x86 specific. So I think we would, sorry.
The concept would be the same.
Yeah. So at a high level, yes, we might refactor the existing unwind hints to reuse them, or we might make that a more architecture specific thing. But yes, I think we would have something of that sort.
For the no return aspect, I wanted to understand if this is something, so as I see it, it looks like it's something usable at this time for the unwinder. Is the no return, you guys were talking about the security aspect too, is this no return annotation something also useful for other use cases in the kernel?
So
If we just, so the intention here is to ask, should this be something annotated in the unwind formats, or should this go wider and get into maybe the object somehow?
Yes,
is where I want to get at.
So that is a good question, and the thing is, I am not certain at the moment what level we need this. The reason that we care for the unwinder is two reasons. One is that for a human, if we're printing out a thing there that isn't actually return address, that's bad. It's just misleading. And two, for the actual live patch consistency model, it just means that like early kernel code, like when you start kthread, etc., that is all no return. It is entirely possible that every thread on the system has a completely bogus return address. And if that happens to be a function we want to live patch, we end up not being able to live patch it at all. So that's the reason we care for that. Whether that should be in the format, I don't know. But
well, I think my partially uninformed opinion or answer to that question, I think, is yes, because we kind of have this issue where, like, sometimes it's helpful to know, is a function no return, right? And anyone who calls it, they're all calling the no, like it's no return for all the callers, right? And so I think in Obstacle, there's a table where we have to keep like a table of like no return functions. And like I don't think there's anything in Dwarf that says like this function is a no return function. And you might even not even be emitting debug info. So like, is Dwarf even the right place to put that? And so right now on x86, we have to kind of encode these out of line. And I just wish there was some way to answer the question universally of like, where are the no return functions in this binary? And you kind of have to like either look at the disassembly or keep an out of line table or something, right? Like
for the no return case, so the stack walker, does it really want to backtrace on the return address or on the actual caller address?
We cannot, so for reliable structures, we want the return address because we want to know where we're about to go to. We cannot reliably get the caller address because in some cases it does not exist.
So this is where I guess the reason why I might be asking is there's two use cases here where one is for debugging, you want to know who called that function. So
Yeah.
you want the caller thing. But for live patching, you want to know where it's going to go back to because you don't care who called it. You care about where it's going to be.
Yeah, and in my view, that's the difference between a return trace and a call trace. And what we have today is a return trace, right?
Oh, well, okay, yes, yes.
So you have to remember that the no returns are like, they theoretically could be lowered to a tail call, a jump. Instead, they're lowered as a call to make unwinding easier, which is like, it's actually harming us in this case.
Yes, so actually that's,
Like if it was a jump, like we wouldn't have this issue where the link register is pointing to the next instruction after the call, which like due to control flow layout, maybe like the beginning of the next function, right? So the current unwinder today sees like the call to the no return, and it looks at the link register is now pointing to the first instruction of the following function. So when unwinding, you're not even going back through the correct like caller. You're going through like the function after the
But
caller.
in this case, can you just offset and kind of say, well, in this
So
case,
just say -4 or
minus
whatever.
4, -1.
So
whatever.
I appreciate that. It's very easy to be lulled into a false sense of security that we
Yeah.
can always do that, whereas we cannot always do that because there are cases where -4 is not
Right.
the call
It-
address.
Like the very first instruction in the function could be a call. And then like if you say -4, you're looking at
Yeah. So the one
the
thing
call
we
function
the
before.
one thing we've done for consistency today is it is a return trace because we can guarantee we can give you that aside from no return.
Yeah, I have a question. So how do you decide that the function is a no return?
We don't have that information today. I'm asking that.
You haven't
That's a
have
thing that we need.
information.
Yeah.
You needed the information from the compiler?
Yeah.
Oh, okay. So what you mean by the false positive of no return? You mentioned a false positive no return in the very beginning of the slides, I remember. So that means the compiler passed some wrong information. It's a
Yes. So the issue was the one that was just described is, say you've got two functions, one after another, and function A and function B. Function A calls a no return function. Because the compiler knows that that is a no return function, that call to the no return function happens to be the last instruction of function A. So now when we go and unwind, and we unwind that no return function, we look at its return address, and it will be the first instruction of function B, even though we're never actually going to return to that. So that's the false positive, that it looks like that function is in the trace, even though it's never actually going to be returned to.
okay.
So I'm almost curious of like, maybe we could have a compiler flag that could change, instead of lowering no return calls as calls, like tail call them. Like, I don't know what the trade-off would be. Like, does that break other stuff? But
So
like, the traditional answer of like, why does the compiler not lower no return calls as tail calls?
it's so you can get a stack trace out. I would prefer the thing that we said earlier about if we have a trap instruction immediately following it.
A trap instruction would be good. Also, I'm like thinking, you have that the thing where you put padding in front of a function for the tracing.
Have it for
Is there a
afterwards.
way to after the function, or at least for like, so if
There
you
is-
just pick it.
So I don't believe there is currently a generic option that's shared by
So-
both GCC and Clang. But
yeah.
So you need the compiler to mark all the non-return function. Or the compiler, if compiler analyze the routine, no return, I think it can do it, but it's do it conservatively. Only the real no return function, it can mark it.
yes.
Otherwise, it will have some
Yeah.
other impact.
Yeah, sorry, I agree. But I think where the compiler cannot tell a function is no return, its caller is going to have to assume it will return. And then we don't have the problem because the return PC will be within that caller.
So
Same way.
if compiler identifies no return function, it must be a no return function. But it's possible that one no return function cannot be. So so if it's a return function, but compiler mark it as a no return, then there's a compiler bug because that will introduce some wrong transformation. So compiler will not do that.
Sure.
Yeah.
Okay, no, time is up.
Okay.
It's lunchtime. Let's move the discussion there. Thank you. Thank you all. Thanks for the great discussion and enjoy the rest of the conference.